Hi everyone, I welcome you all to my channel Knowledge Center. Today we are going to start the first chapter of analog electronics, that is diode circuit. So before jumping into the technical point of diodes, let us understand the history of diode, how actually the diode has invented, who all plays an important role in the discovery of a diode. So there is an interesting story behind the invention of a diode, because just not one or two persons are behind this story of a diode. There are so many scientists who worked on this diode. So let's have a look over the history of a diode. There are actually two types of diodes which we need to discuss now. That is, the beginning concept we have thermoionic diode, and later on we got the semiconductor diode. We are all familiar with the semiconductor diodes, and those semiconductor diodes are presently used and they are famous. Okay, so before semiconductor diodes there was a thermoionic diode which was very famous. So now let's see how and what was actually the history of thermoionic diode. So on board I have mentioned here few points so that you can just have a note over there. And this is not going to be asked in any competitive exams or even a general engineering or a diploma degree, but you need to have an idea of concepts which we are discussing in future. Okay, so now let's look into that story. So in the year 1873, the research has started in the year 1873 by a scientist called Frederick Guthrie. He has given the basic principle of thermoionic diode. The first person who has given the basic principle of thermoionic diode in the year 1873. Later, in 1880, the great Thomas Alva Edison, in the year 1880, Thomas Alva Edison had an observation that an unidirectional current is flowing from heated element to unheated element in a bulb. That is what his observation. During his research, he observed that unidirectional current is flowing from heated element to unheated element in a bulb, and he named it as a Edison effect. You can have a look here. This is important. He named it as an Edison effect, and he got even patent for that, for Edison effect. Later, about 20 years later, one more scientist, that is John Ambrose Fleming. We know him as just a Fleming, but his full name is John Ambrose Fleming. He realized that the Edison effect can be used as a radio detector. Edison effect can be used as a radio detector, and he got the patent, the first true patent on thermoionic diode. He named it as a thermoionic diode, and also it is named as a Fleming valve. So the research was started in the year 1873. Almost after, in 1880, Thomas Alva Edison given a new effect for that, that is an Edison effect. Later, Fleming, John Ambrose Fleming, has discovered it as a radio detector, and he named it as a Fleming valve, and he got patent in Britain on November 16 in the year 1904. So this is important. In the year 1904, we got this as a thermoionic diode. So this is just a story how we got the thermoionic diode. The same way, when in 1873, when there was a research on thermoionic diode, there was also a parallel research was going on semiconductors. Okay, so let's have a look over that, because that semiconductor has given us a semiconductor diode. So now I am going to tell you how that semiconductor diode has been obtained. If we look into the history of semiconductor diode, it is also started in parallel with the thermionic diode. As I told you, in thermionic diode, it was started in the year 1873. Similarly, here the semiconductor diode evaluation or the main research started in the year 1874 by a great German scientist Carl Ferdinand Braun. So Carl Ferdinand Braun has given the basic principle on operation of crystal diode. He has given the basic principle of operation of crystal diode, and he got patent on that in the year 1899, and that was the basic concept to develop the semiconductor diode. Okay, so later this concept of crystal diode has been developed by an Indian Jagdish Chandra Bose into a useful device, and that is named as a radio detection. Okay, he has developed it, utilized this concept and developed it as a radio detecting device. But Greenleaf Whittier Pickard, I understand this name, a Greenleaf Whittier Pickard is a scientist who got the patent on this radio detection concept, because Jagdish Chandra Bose did got the patent on that, but he developed it, and later Greenleaf Whittier Pickard got patent on November 20 in the year 1906, and this is the era where thermionic diode was losing its market, because these crystal diode was having very important advantages compared to the thermionic diode. So in this era, thermionic diode lost almost its market. Okay, later William Henry Eccles coined the name diode. Later on it was just started calling as a diode instead of thermionic, crystal diode, radio detector, just named as diode, and that name has been given by William Henry Eccles in the year 1919. Okay, so many names we got in between this research. It started from almost year 1873 and ended up 1919 to get the name as just diode. And here this diode is the word taken from Greek roots. Okay, it's taken from the Greek language, and I hope you know what actually the diode is. Let me tell you. Diode means their Di, that stands for di. So this is nothing but 2, because diode will have 2 terminals. I'll just tell you when we go to the technical point, but also I'll tell you what is the meaning of the name. Di stands for 2, and ODE, diode, right? ODE is a shorthand of electrode. It is just a shorthand of an electrode, or it is also known as path. It's a path for a flow of electrons. So this is the history of diode. It started in the almost year of 1873, and we got it the exact name of diode in the year 1919 by William Henry Eccles. I hope this is very important information you got. If you like this, just hit the like button over there. Now let's move on for the technical point of a diode. Now let's have a technical point of diode. So before defining the diode, first let us say how it is made up of. So it is made up of, as we all know, diode is made up of a PN junction. So we take P type of element, and that will be joined with N type of material element, and when we combine P and N element together, there will be a junction framed in between P and N, right? So then that's the reason why we call it as a PN junction, and this PN junction is known as diode. The PN junction is known as diode. So the reason of PN junction is, we all know that N is nothing but it's a N type of a semiconducting material, and this is a P type of a semiconducting material. When we join those two, and if I apply some electrical force, then the current will be flowing in the device, right? So diode is nothing but it is going to allow the flow of electrons, right? But there are some conditions, there are some limitations. So before going to take a definition, let me explain you the picture of it. Okay, so this is P and N, and I told you that we need to collect the current. So for that we need to have some metals or some elements to collect it. So we connect an electrode here, and that electrode cannot be connected directly. So we will have a ohmic contact which will have very low resistance. That's why it is called as an ohmic contact. And this ohmic contact, for this ohmic contact we will connect a electrode. So we will have 2 electrodes. We got 2 electrodes. One is for P and another is connected for N type of material, and these 2 are named as ohmic contact. You can understand it like this: ohmic contact, which is going to have very less resistance. So this is a ohmic contact, right? So now we can define with respect to the structure that diode is a 2-terminal electronic device which allows the current in only one direction, and it will oppose it in another direction, right? It's a two terminal device, allows the flow of current in one direction and opposite it in another direction, right? So let's see how actually the current will flow and what actually is going to happen. That is the next concept we are going to look into, right? So before that, let's understand what is this P type of material and what is the N type of material. How do we get it? Okay, those two are just semiconductors, right? So now P type of semiconductor is nothing but that is the material which we use here is either a boron, right, or gallium. So this is the material used for P type of semiconductor, and for N type of semiconductor we use either arsenic or phosphorus. So these are the materials which is used for P and N type of semiconducting devices, and then we frame it together to get a PN junction diode. Okay, so now let's have a look of symbolic representation. This is just how it looks, but this is not the symbol of diode. So let's have the symbolic representation of diode. So this is how diode looks like. Means symbolically we represent it. Okay, and there are two terminals. We need to give a name for that, right? The element where we have P element, this portion we name it as an anode, and this portion we name it as a cathode, or we can write it like this. P region will be named as anode and N region will be named as a cathode. Okay, so this is A and this is K, that is the representation of anode and cathode electrodes. Okay, so this is diode. I hope it's clear. The definition of diode will be now, it is a two-terminal electrode which allows the flow of current in one direction, whereas it opposes in the another direction. Now we will understand why it is going to oppose and how it will allow. That concept will be understood within a few minutes. Okay, so now before going to that concept of working of a diode, I want to tell you one more important thing, that is this is just like a arrow mark. The diode symbol is just like arrow mark, right? And this point, this we call it as a head. This we may call it as a tail. So the head indicates, this is going to indicate the flow of conventional current. Flow of conventional current in the diode. Flow of conventional current in the diode. So the head indicates the conventional current of the diode. Okay. This is about the PN junction and the symbolic representation of a diode. Now let's see how the current will flow, what actually happens in that PN junction. Okay, so let's have a look over that. So PN junction, as I told, it is a semiconducting device. So if I take a picture like this, so it will be easy for you to understand. Say P. The P type of material will have the major carrier as holes. So holes are nothing but positively charged. So you can have the picture like this. I can have holes here, right? Whereas N type of material is nothing but the majority carrier of N type of element is electrons. So we can represent it like this, negatively charged. So this is what going to happen here. We have a junction, and I have holes here and have electrons here, major of electrons. This is N region and this is P region. That's why we name it as a P region and N region. Now if you don't give any supply and all those things, let's understand what's going to happen in this PN junction. Okay, say this is a ohmic contact and there is an electrode here. This is ohmic contact, there is an electrode, and assume that we have not given any supply. Supply is not given to this PN junction. Then what happens here? See, if supply is not given, if you just frame that PN junction together, we have a positive terminal here or a positive hole here, and this is the negative, and it's a basic principle that opposite parts will be attracted towards each other. So this positive will be jumping towards the N region, and this electron will come towards P region. So there will be exchange of holes and electrons, but that exchange will be taken place only to the electrons and the holes which are nearer to the junction. So say these are nearer to the junction. Only these electrons will come here and these holes will move towards this region. That change will take place. Okay, so if I represent it, if I redraw it, it will be like this. I'll draw it here. So if I take P here, now we will have positive here, but here we are going to have the electrons because of the general concept for nature is positive and negative will be attracted. So these are going to be shifted by the region. So N region, and there will be change in N region and a P region. So you can compare this picture with this one. Okay. Right, we have electrons here. So look into this. This is P and this is N. But now what happened? We got the change here. Look at this picture now. We got electrons here and we got the holes in the N region. So that will be going on. It will not going to be stopped over there. Once after getting this, again we have electron here and we have hole here. So this will be again shifting towards this side and electron will be moving towards this side. So that change will be taking place continuously. It will be there continuously, right? There will be no break for that. So there will be a electric field because we have a movement of electrons over there. So there we get a electric field, right? And this region is called as a space charge region. So this is most important term which you need to understand here. There will be a space charge region created in the PN junction. Okay, and because of the movement of these electrons and the holes in that space charge region, there will be an electric field, right? And because of the movement also we get a current. That current we name it as a diffusion current. It's a diffusion current. The current which we have in a space charge region is termed as a diffusion current. But yes, we got a current here, but that current is not passing these electrodes. It's not passing through the electrodes. It is not coming here. It is just in this region only, right? So there is a voltage here, there is a current here, but it is not coming out of those. It is not collected by the electrodes, right? So it is no use of it, right? So to break this, we need to break this barrier. This is a barrier. So in some textbook they name it as a barrier voltage, or we call this as a knee voltage or a threshold voltage. So we need to break this now. When we place that PN junction together, this barrier will be created automatically. So we need to break this. Once if you break that, then electrons and protons, electrons and holes will be moving and we get the flow of current, right? So we need to apply a minimum voltage which is similar to this, which is equal to this. We need to break down this. Once you break down this, then there will be a flow of current. So that is the reason why we give a external force to the diode, right? So, and you might have an idea that you need to give a knee voltage 0.3 for silicon. If it is a silicon diode, you need to give 0.3 volt. After 0.3 volt, it will start conducting, right? It means what? That 0.3 volt is required. That is the required voltage to break this space charge region. We need to apply some minimum voltage which is going to break this space charge region. So once you break down that, then there will be a flow of electrons. So that is nothing but the current. So now, I hope you got very clear concept about what is the space charge region and what is diffusion current and what is the voltage we get in that space charge region. So that electric field can be named as a knee voltage or threshold voltage. So some of the, based on the textbooks, some of based on the authors, they name it like that. Threshold voltage, okay, or barrier voltage, because that is creating a barrier over there for the flow of current, barrier voltage. So we need to apply that barrier voltage, okay, minimum that is required. Until and unless you give that minimum voltage, diode will not conduct. So now let's see how to give that supply, okay. So there are again two possibility of giving the supply for the diode, that is in forward region and in reverse region. So let's have a look over there. Now for the same picture, here I have the diffusion, that is we have a space charge region, okay, or depletion layer. We call it as a depletion layer also. Now let's say there is a ohmic contact and there is an electrode. Here one more electrode we will have. For this electrodes, now let us connect the battery. Okay, if I connect a battery which is of positive terminal and negative terminal as shown in this. So if I give the positive terminal here, okay, so what happens? Okay, let's see, there is a positive terminal. It is just, we have positive term, we have holes here, we have plus terminal here, and we have electrons here, we have negative terminal. Now you tell me, if I give a negative terminal here and here also I have a negative terminal, will they attract or will they repel? When we have a same polarities, it will repel. Okay, so when I give negative terminal to N region or cathode, we name it as a cathode. Okay, and we name this as a anode. So when you give negative terminal to cathode, here also we have a negative, so it will be repel. It will just push that negative towards this. It is repelling. It is not attracted towards this terminal. Same thing happens with this. Positive is given for the positive charge holes, so these are also going to be repelled. So it is just pushing this. Okay, here electrons are moving towards this direction. Here holes are moving towards this direction. That will just narrow down the region. Which region? Space charge region. Okay, so it will just narrow down the space charge region, and you just go on increasing this polarity of voltage, and at certain voltage it will be narrowed, and it will just allow the flow of electrons from anode to cathode. Okay, so the conventional current direction will be this conventional current from higher polarity to lower polarity. This is the conventional current direction. So this is how it works in the forward bias. We name it as a forward bias. This we call it as a forward bias. So in forward bias, what actually happens over there? We are narrowing the space charge region, okay, and we are just allowing the electrons to flow, and the conventional current will be taken like this. Okay, so it is just rippling and it is narrowing. Now the same circuit, if I reverse it, let's see what's going to happen. Now I'll draw it again here with the PN, and we have a positive, electron. So we have electrons at the junctions here in P region. Now don't say, sir, only these number of electrons will be there or what. So just for a rough picture, I am just drawing it. You may have n number of electrons. It depends upon the what type of an element we are using, right? So now for this type here, if I give a reverse polarity, what's going to happen? Let's look into that. Say I give negative here and positive here. So we have plus, minus, and this is the region we have. This is the space charge region or a diffusion layer. This is N type, this is P type. Now when I give negative, here we have positive, right? So this name this as anode and cathode. See, if I give negative terminal to anode, right, what's happening here? Minus, and we have plus here, so it will be attracted. These holes will move towards this. It will be attracted, right, attracted to this polarity. Whereas here plus, and I have electrons negative here, so these electrons will also move towards this. What's happening here? It is just increasing. It is elaborating the region. Space charge region is getting expanded. It's getting expanded. It is not narrowed. So that is the reason why we call, when we apply this reverse kind of a polarity, diode will not conduct, because it's just increasing the region over there instead of narrowing it. Okay, so it will be expanded, but there is a limit for that. Okay, if you go on increasing this reverse polarity, then what happens? These electrons will jump to this region of P, and these holes will jump to this region of N, and that we call it as a breakdown. So when we go on increasing the reverse polarity, breakdown occurs. So there we call VBD or breakdown voltage. So we need to be very careful about voltage. Now let's understand the same concept, the working concept of it, using a graphical representation. Okay, so we call it as a characteristics of a diode. We can just understand this, whatever the explanation I have done here, same thing we can represent it using a graphical picture. Let's see how to do that. To represent that, we need to have all the parameters, like we have the voltage in forward bias, voltage in reverse bias, the current flowing in the forward bias, current occurs during the breakdown in a reverse bias. So all those parameters should be there in a graphical representation. To do that, I will have a graph here. So let me take it like this. Say this is Vf, which indicates the forward voltage, which we do give in a forward bias. In reverse bias, we give the reverse voltage. So let me represent this as a Vr, that is reverse voltage, and we will get the current in forward bias, that is forward current, and we also get the current in reverse bias, named that as reverse current. Okay, so we get current in reverse bias only if there is a breakdown voltage. Okay, now we have some more parameters, that is VBD and VT or VK, that has to be represented here, right? So VK is nothing but what? That is the knee voltage. Now look into this forward bias. If I give 0 voltage, now we won't get the flow of current easily, right? There will be just 1 or 2 electrons will be moving, but we won't get the full flow of current over there, right? So that we need to represent it in the graph. So to that I will take another marker. Okay. When we give 0 voltage and when we give the voltage which is less than Vk, or we can write it like this. If forward voltage is less than the threshold voltage, if forward voltage is less than the threshold voltage, the diode will be not in conduction. It is not in conduction. So do it like this, right? It is an off condition. So current will not be flowing, right? So small current of number of electrons will be there. So we can just represent it like this and say this is new voltage or a threshold voltage. Let me denote it as a VTH, threshold voltage. Okay. So once we cross this threshold voltage, once Vf becomes greater than or equal to threshold voltage, then the diode is going to be on. Diode is on, right? So when diode is on, current will flow and it will be exponentially increasing because there will be a flow of electrons from anode to cathode, flow of current from anode to cathode. So this is how we can represent the graph. This happens in forward bias, whereas when you consider the reverse bias, okay, here we won't get that threshold voltage, we get the breakdown voltage. Until we reach that breakdown voltage, we won't get any flow of current. So it will be like this, slowly it will be moving. Say this is breakdown voltage. So at that point, when we reach that breakdown voltage, if we are going beyond the breakdown voltage, if increasing the voltage beyond that, then there will be a short circuit. Breakdown occurs, nothing but short circuit. There is no opposition at all. Flow of current will be there, heavy flow of current. So that will be increasing like this, but in a reverse direction. So this is the characteristic of a diode, graphical representation of a characteristic of a diode. Okay. And now, before leaving and before stopping this class, I just want to give you one important point. So that is, when do you call that diode is in forward bias or it's on, and when do we call that diode as off condition? Let's have one simple example on that here. Okay, I'll make one action I'll take here, or one task I'll give, which will be very most important to understand the clipper and clamper circuits. Okay, till now I think you might have a definition of forward bias. Now I'll give the definition of forward bias. So that is most important for us. So forward bias means, generally people say that when anode and cathode, if they are like this, if anode is at positive terminal and cathode is at negative terminal, then we name it as a forward bias, means diode will be on. Yes, that's true, right? But this is not the 100% perfect answer. It's true, I'm not saying it's wrong, it's correct, but it is not the 100%, because if I say, say now I'll take the diode and I give here minus 1 volt and I give minus 3 volt. So here, according to this, minus 1 is here at anode and minus 3 is given at cathode. Now tell me whether this diode is going to be turned on or off, means whether it is in forward bias or reverse bias. Okay, you tell me that. Think about it. Here we have negative, both the case we have negative voltage, but this is greater than this, minus 1 is greater than minus 3, right? So we can say anode is at higher potential than cathode. Cathode is at lower potential. So this diode will be on. There will be flow of current. This is in forward bias. So it doesn't matter about the direction, whether minus we are giving, plus we are giving. No. It's all about whether we have a higher potential at anode or not. If we have a higher potential at anode, then diode will conduct. Right? If you understand this funda, it will help you to solve the clipper and clamper concepts easily. Right? Don't just stick with this condition. This is suitable for only rectifiers. This definition is suitable for rectifiers. But when you go for clipper and clampers, this will create a confusion for you. Right? Sir, so that's why you should understand this. Anode will be always, the diode will be understood in this concept. Forward bias means if anode is having a higher potential compared to the cathode, then we call it as a forward bias. You can take the definition like this. Okay? And if anode is at lower potential compared to the cathode, then that is a reverse bias. So this is most important funda. That's why I just given at the end of the video. Watch complete video, right? And if you think it's very clear for you, if it is clear, just press the like button and share among your friends. Thank you.